the very last circuit of the year is again an LC circuit. So I've got an inductor and a capacitor in series. And what I've done is I've got this switch here, so that I was able to move the switch over, charge up the capacitor so it looks like this, a plus and a minus as it was connected to the battery. And then I flip the switch over, and now I'm using the capacitor to run my LC circuit. Okay, so it's kind of like a capacitor discharge. But let's see if it's going to discharge fully or what's going to happen here in an LC circuit. So of course, when I connect the capacitor with the inductor and I've removed the battery, charges are going to want to flow that way. The capacitor is going to try to force charges onto the inductor, or through the inductor, really, it's going to try to force current. But at the beginning, of course, just like when the battery was trying to force current through the inductor is going to win at first. So at t equals 0, we have a current of 0. So if I want to go ahead and do a Kirchhoff loop rule, I need to figure out the plus and the minus on the inductor itself. And it's going to have to oppose the capacitor. One, because we know that's what the inductor wants to do, but also because we know that the sum of the voltages have to add up to 0. So it has to be opposite the capacitor at all times. Okay? So I'm going to go ahead and do a clockwise loop rule. And it's going to look something like this across the capacitor, because my loop is going from negative to positive, and that's going to be a gain of Q over C. And then as I go across the inductor, it's going to be a drop of L di dt. And again, those have to sum up to 0 according to Kirchhoff's rules. Great. I'm in the same position I was before with the LC circuit, and that is the small factors, di and dt, don't match the only variable that I have. So that is going to be a challenge. The one thing I want to point out up here, again, remember that the current flowing through the system is a result of charges coming off of the capacitor. These are not new charges added to the system, right? These are charges coming off the capacitor. So in order to get current, I have to just discharge the capacitor. So what I'm going to do, just like in the LC circuit with a battery, I'm going to cheat a little bit and take a derivative of this entire equation. Take a first derivative with respect to time. Okay? So over here I have 1 over c, because that's a constant term, and it leaves me with dq dt, taking the derivative of charge, minus L is also a constant term, so I can pull it out, and I have the derivative of current, which gives me the second order derivative with respect to time. Okay? Just like last time with the battery, I needed to find a way to turn this into a variable that will match the small factor. But remember, what we set up here is that the current is due to charges leaving the capacitor. So that means that dq dt is minus the current I. So I have minus 1 over ci minus L times the second derivative of current with respect to time is equal to 0. Okay, so I'm going to go ahead and solve this for the derivative. So 1 over ci is equal to L times the second derivative of current with respect to time. And I want to get rid of that L to isolate the derivative. So I get minus 1 over LC times the current is equal to the second derivative with respect to time. Okay? And this is the exact same result as what we got when the battery was in. This, again, is simple harmonic motion. So I've taken the battery out, and somehow I have the current passing back and forth, right? It's going to look like a sine wave, just like it did for the LC circuit with a battery, right? And you're thinking to yourself, how is that physically possible? I've taken the battery out, I've taken my energy source out. How can these two, this capacitor and this inductor, keep passing charge back and forth? Well, practically, they can't. Eventually, they're going to run out of energy. If we don't have a battery in there to restore any of the energy that's lost through the resistance, then it is eventually going to run out. It would be more realistically, it would be like a damped oscillation, where the amplitude keeps getting smaller and smaller and smaller. But for perfect capacitors and perfect inductors, where there's no resistance internal to the system at all, then we are expecting here simple harmonic motion, just a sine wave for the current. It's fluctuating between some positive and some negative amplitude. Okay. All right. Again, this is Mr. R signing out. Stay classy or not. Just do whatever you want.